Good morning. In today's lecture, we discuss about the closed graph theorem. Not all the linear operators of practical importance are bounded. For example, the differential operator is unbounded, and in quantum mechanics and other applications, one needs unbounded operators quite frequently. However, practically all of the linear operators which the analyst is likely to use are so-called closed linear operators. This makes it worthwhile to give an introduction to these operators. So now we define closed linear operators on norm spaces and consider some of their properties in particular connection with the important closed graph theorem, which states sufficient condition under which a closed linear operator on a Banach space is bounded. So let X and Y be norm spaces and T is a mapping from domain of a T to Y is called a linear operator with the domain of a T subset of AX. Then T is called a closed linear operator if its graph G of T is a collection of all those xy such that X belongs to be domain of a T and Y belongs to be Tx. Is closed in the norm space X cross Y, where two algebraic operations of a vector space in X cross Y are defined as usual, that is x1 y1 plus x2 y2 is equal to be x1 plus x2 comma y1 plus y2, and alpha times xy is equal to be alpha x alpha y, where alpha is scalar, and the norm on x cross y is defined as norm of xy is equal to be norm of ax plus norm of ay. So now we have a question that under what conditions will a closed linear operator be bounded? So its answer is given by the following result, which is a closed graph theorem. So let X and Y be Banach spaces and T from domain of a T to Y be a linear operator with the domain of a T is a subset of AX. If this domain of a T is closed in AX, then the operator T is bounded. So now we'll discuss the proof of this theorem. We first show that the norm X cross Y defined by norm of axy is equal to be norm of ax plus norm of y is complete. So let Zn be any arbitrary Cauchy sequence in x cross y, where Zn is equal to be x and yn. Then for every epsilon greater than 0, there is an n such that norm of a Zn minus Zm, which is equal to be rewriting the terms like a xn yn minus xm ym, which is equal to be xn minus xm comma yn minus the ym, and using up the property of a norm out here, which is equal to be norm of a xn minus xm plus norm of a yn minus ym is less than epsilon for all m and n greater than or equal to be n. Hence, from this we can say that this sequence xn and this sequence yn are Cauchy in x and y respectively and converge because x and y are being given to us as a complete. So xn converges to be x and yn converges to be y. So this implies that the Zn converges to be x comma y, say that it's equal to be z. And since with m converges to be infinity, we have this Zn minus z is less than epsilon for all n greater than n. And since the Cauchy sequence Zn was arbitrary, so x cross y is complete. In our assumption, gt is closed in x cross y and dt is closed in x, hence gt and dt are complete. So we now consider a mapping P from a graph of a T to the domain of a T defined as the mapping this. Here it is easy to be checked that this P is a linear and 1 1. Also P is bounded because here the norm of a P of Ax comma Tx is equal to be a norm of Ax by the mapping out here. which is less than equal to be norm of ax plus norm of a tx, and using up the norm defined over here, it is equal to be norm of x comma tx. So here P is a bijective. Inverse mapping is being defined as a P inverse from a domain of a T to the graph of a T as this. And since GT and DT are complete, so by the bounded inverse theorem, we have a P inverse is a bounded. And say the norm of Ax comma Tx is less than equal to B times norm of Ax for some B, and X belongs to be domain of a T. Hence, T is bounded because the norm of a Tx is less than equal to be norm of a Tx plus norm of Ax. By the definition of a norm, this is equal to be norm of Ax comma Tx, and here we said that the norm of Ax comma Tx is less than equal to be B times the norm of Ax. So norm of a Tx is less than equal to be B times the norm of Ax, where all x belongs to be Tt. So by definition, so here we have proved up that is having a bounded under the given condition. So by the definition, graph of T is closed if and if only z is equal to be xy belongs to be a closed g of t. We implies that z belongs to be gt. Also we see that the z belongs to be a closure of a g of t if and only if there is a some zn belongs to be g of t such that zn converges to be z. Hence we can say that the xn converges to be x and txn converges to be y. And z is equal to be xy belongs to be graph of a t if and only if x belongs to be domain of a t and y belongs to be tx. This proves the following useful criteria which expresses a property that is often taken as a definition of a closeness of a linear operator. So what is that definition is here? So let T is from domain of a T to Y be a linear operator where domain of a T is a subset of Ax and X and Y are norm spaces. Then T is a closed if and only if it has the following property. But the property is if Xn converges to be X, where Xn belongs to be domain of a T and T of X converges to be Y, then X belongs to be domain of a T and T of X is equal to be Y. So this property is different from the following property of a bounded linear operator, which is different from the definition of a continuity. If a linear operator T is bounded and thus continuous, if Xn is a sequence in a domain of a T which converges in a domain of a T, then sequence Txn also converges. This need not hold for closed linear operator. However, if T is a closed and two sequences xn and yn in the domain of a T converge with the same limit, and if the corresponding sequences txn and tyn both converge, then the latter have the same limit. So for example, we will discuss up here using about this proposition. So let x be the set of a closed set of the continuous real valued functions on the closed interval 0 1, and t is from domain of a t to x defined as x is equal to be maps to be x dash, where prime denotes the differentiation and domain of a t is a subspace of the functions x belongs to be x which have a continuous derivative. Then t is not bounded but is closed. Here t is not bounded as if I consider the x and t as a polynomial t n, norm of a xn is equal to be 1. So t of x and t is being defined as a x dash of n, which is equal to be n times the t raised to n minus 1. So the norm over the txn will be considered to be n because the norm over t is equal to be 1. And hence the norm of a txn over the norm of a xn is equal to be n, where n is arbitrary. So there is no fixed c such that the definition of a bounded linear operator is being satisfied. That is the norm of a txn over the norm of a xn is less than or equal to be c. So differentiation operator is not bounded. So now we will prove that T is a closed. So let xn be a sequence in a domain of a T such that both sequence xn and txn converge. Say xn converges to be x and txn converges to be y. And txn is equal to be xn dash. Prime xn is there. Since convergence in the norm of a continuous real valued function in the interval 0 to 1 is uniform convergence on the interval 0 1. So from xn prime converges to by, we have integral of 0 to t y tau t tau is equal to b integral 0 to t xn prime limit n converges to be infinity, which is equal to be limit n converges to be infinity 0 to t xn prime, and which is equal to be x of t minus of x of 0. And thus we have x of t is equal to be x of 0 plus integral 0 to t y of tau t tau, and this shows that the x belongs to be domain of a t, and x dash is equal to be y, because here the domain of T is a subset of C01, the set of all functions x which has a continuous derivative. Hence, T is closed. So it is worth noting that in this domain of a T is not closed in X, and since T would then be bounded by the closed graph theorem. So closedness does not imply the boundedness of a linear grid, and conversely, boundedness does not imply the closeness. For example, T is from domain of a T to the domain of a T, subset of AX. We add an T operator on the domain of a T, where domain of a T is a proper dense subspace of a norm space X. Then it is trivial that T is a linear and bounded. However, T is not closed. This follows from the closed linear operator theorem if we have take the X belongs to be X minus domain of T and the sequence Xn in a domain of T which converges to X. So now we have a closed operator. Let T is from domain of T to Y be a bounded linear operator with domain of a T is a subset of AX, and X and Y are norm spaces. Then if domain of a T is a closed subset of AX, then T is closed. Number two, if T is closed and Y is complete. Now here if we took the completeness of a Y, then the domain of a T is a closed subset of AX. So first of all, we'll discuss the part A. If sequence Xn is a domain of a T and converges, say xn converges to be x and such that the txn also converges, then x belongs to be a closure of a domain of a t. And since the domain of a t is closed, so closure of domain of t is equal to be domain of a t. And thus txn converges to be tx since t is a continuous. So hence t is closed. For the second part, if t is a closed and y is a complete, then domain of a t is closed subset of x. So for x belongs to be closure of a domain of a T, there is a sequence xn in a domain of a T such that xn converges to be x. And since it is given to us that the T is a bounded, so norm of a Txn minus Txm is equal to be norm of a T of a xn minus xm, which is less than equal to be norm of a T into norm of a xn minus xm. And this shows that the Txn is a Cauchy. And also it is being given that the y is a complete, so this Cauchy sequence converges to y. So say let txn converges to be y. And since t is a closed, so x belongs to be domain of a t. And hence domain of a t is closed because x belongs to be closure of domain of t was arbitrary. So here in this lecture we have discussed some of the properties in related to a closed graph theorem. Thank you.